Drew. In this video, we are going to start looking at finding derivatives of functions dealing with the natural log function. And like all my videos, there's going to be lots and lots of examples, so hopefully this one video will get you through pretty much your entire assignment. The natural log function differentiation. Well, here we have the power rule for integrating. And there's a type of function we actually haven't done indefinite integration with yet, and we're not going to in this video, but over the next couple of sections in our book, we're going to see the relationship which is going to allow us to do this. The indefinite integral of x to the n dx is equal to x to the n plus 1 power divided by n plus 1 plus c. But the condition for using this was that n could not equal negative 1. Well, if you try and find the indefinite integral of 1 over x, that actually ends up happening. You have the indefinite integral of x to the negative 1. You raise that by 1, you get x to the 0 power divided by negative 1 plus 1, which is x to the 0 power divided by 0, which is undefined. So we're going to see how we're going to be able to find this indefinite integral over the next couple of sections, but right now we're just going to deal with definite integrals and this relationship between the natural log function and the function of basically 1 over y equals 1 over x. So our definition of the natural log function is the natural log of x is equal to the definite integral from 1 to x of 1 over t dt. Now, again, I said the second fundamental theorem of calculus, or think I did over here, is coming up, and so we're going to see how this variable changes, unless you remember, of course, from the second fundamental theorem of calculus. But anyway, definite integral from 1 to x of 1 over t dt, where x is greater than 0. And what it says, or what it shows us here, is that we have, at least as far as the domain of x greater than 0, we have the function of y equals 1 over t. And the natural log of x is equal to the area bound between that function of y equals 1 over x and the lower bound of 1 and the upper bound of x. So the area between the x-axis and our function, between 1 and that upper limit of x, is going to be, that area is going to be the natural log of x. And so if we're beyond the value of 1, that shows with this definition that the natural log of x is going to be positive. If we find the definite integral where at 1, where the lower and upper limit are both equal to 1, then right here, then our natural log of x is going to take on the value of 0. And then if we're to the left of 1, we still have an area, but because our lower bound is greater than our upper bound, and we talked about how you could switch those lower and upper bounds and create an opposite answer, it shows that the natural log function is going to be negative when x is between 0 and 1. Excellent. So over here we have the definition, or let's talk about e, because we're talking about natural log, and of course natural log is the log base e. And if you're not really familiar with or comfortable with logarithms, remember they just give you an exponent. Like the log base 10 of 100 is equal to 2, because 10 squared is 100. So exponential functions and log functions are basically inverses of each other, which hopefully you learned in either Algebra 2 or Pre-Calculus. I know my students did. So the natural log is just log base e. So when you take the natural log of a number, what you're getting is an exponent such that e to that exponent is equal to the value of what you're taking the natural log of. So the letter e, which is approximately 2.718, there's a lot of derivations of where it comes from. It's a constant. It's kind of like pi, but that's a lot easier to understand and explain. Just pi is the ratio between the circumference of a circle and the diameter. But one way of defining e is the letter e denotes the positive real number such that the natural log of e is equal to the definite integral from 1 to e of 1 over t dt, and that is equal to 1. So basically, if you start at your lower bound of 1, you go out to your value of e, which is 2.718, the area bound between the x-axis and the function y equals 1 over x is equal to 1. All right. I started to go off on a bit of a tangent, but I want to take care of this definition of the natural log function first. We have, let's see here, the natural log of x, again, equal to this definite integral 1 over t dt. So if I want to find the derivative with respect to x of the natural log of x, we have the derivative with respect to x of course, again, the definite interval from 1 to t of 1 over t dt, Now that's equal to, is this looking familiar? It's the second fundamental theorem of calculus. We have a lower bound, which is, or limit, which is bound, which is a constant, and our upper bound is a variable. I can take that variable and simply drop it into our function and rewrite it as 1 over x. So the derivative with respect to x of the natural log of x is 1 over x. So if you wanted to, graph the function y equals the natural log of x, this function of y equals 1 over x is going to give you the slope of the natural log function at a particular point. Pretty cool. Now, if we, and we're also going to talk about in the next section how the natural log function is the antiderivative of 1 over x, getting to this original problem, which I kind of pointed out we haven't dealt with yet, but we're not going to be dealing with integration in this video. Not quite straightforward because these have different domains. This has a domain of all real numbers except x can't be equal to 0, and this has a domain where x has to be greater than 0. You can't take the natural log of a negative number, or any log of a negative number. So, anyway, getting the chain rule in here, we get the, if you don't have just a basic x here and you want to do a u substitution to make the function look simpler so it's, more easily, you can more easily take the derivative of it. We have the derivative with respect to x of the natural log of u. So we're talking about a u substitution, so I'll have a u here. That's equal to, instead of 1 over x, 1 over u. But since we've done a u substitution, then we have to multiply by the derivative of u with respect to x, or basically get u prime over u. This is really, really powerful, and you're going to have some pretty condition that u is greater than 0. You're going to have some pretty nasty looking problems that, this is going to allow them to be pretty straightforward when finding derivative of functions with the natural log in them. Now, of course, it's calculus. We're always going to have some problems get quite complicated, dealing, power rule, quotient rules, having some radicals we have to simplify, trig functions, but it really does make finding these derivatives with natural log functions at least a lot easier than they could be. Pretty relatively easy, we'll call it that. Now, before we get to some examples, I want to remind you of some properties of logarithms and such so that you can work out these examples. So one more page of notes before our first example. Properties of natural log functions. Your domain for the natural log function is going to be from 0 to infinity, and don't forget that round parentheses means that 0 is not part of the domain, it's not inclusive. And the range goes from negative infinity to positive infinity. So your natural log function is going to come up against the, just to the right side of the y-axis, pass through the point of 1, 0, and then go off to the right. It is going to be continuous. It's going to always be increasing, the parent function, and it is going to be 1 to 1, which means that that function would pass not only the vertical line test to validate that it's a function, but a horizontal line test as well, which means that if you were to find the inverse function, it would also be 1 to 1, at least as far as the domain goes, as that original domain goes as being from 0 to infinity. And the graph is concave downward. I'm going to go through 8 examples. I'm not going to work through every single one of them in very small individual steps because you'll recognize a lot of the skills and the steps that we're doing, which is just basic finding derivatives and using the product rule and quotient rule and such like that, general power rule. But you are going to see me use these properties of logarithms that hopefully you look at this and recall them from either Algebra 2 or pre-calculus. I'm going to do so many examples. I'm not going to just do any work with just these properties purely as if they were in Algebra 2 or pre-calculus. You'll see them as we do these derivative problems. But the natural log of 1 is equal to 0. The natural log of AB, so you're taking these two items and multiplying them together inside the log function. Well, that's equal to the log, or the natural log of A plus the natural log of B. Again, just like I said a few minutes ago, when you log a value, or a natural log of value, or any base for that matter, you get an exponent, right? Like, again, the log base 10 of 100 is 2 because 10 squared is equal to 100. So we're dealing with basically exponents here. So when you multiply with like bases, that like base being the e, which is the base of the natural log, you add those exponents. And of course we have the power rule. The natural log of a to the n is n times the natural log of a. We can take that exponent that's, again, inside the math function of the natural log and move it down out front as a coefficient. much like the power rule is for your exponents. And then when you have the natural log of a divided by b, well, just like when you divide with like bases, you subtract the exponents. We have the natural, losing my balance there, we have the natural log of a minus the natural log of b. Okay, one last rule, if you will, for doing derivatives, which I probably should have included in the previous page, is the derivative involving absolute value. If u is a differentiable function of x, again we're talking about that u substitution that we'll be needing with most of our examples, actually basically all of them, such that u is not equal to 0, then the derivative of the natural log of the absolute value of u, and we get this somewhat often because, again, your domain for the natural log function is only from 0 to negative infinity, so if you have to make sure sometimes that what you're taking the natural log of is positive, because if it's negative it would be undefined or not within the domain of the natural log function. And that ends up just being u prime over u. Alright, we've got lots of examples, let's get to those right now! Find the derivative of the function. So we're going to do 8 examples and start off, of course, easy and go to harder as we go through. And we have f of x is equal to the natural log of 5x. Well, we don't have just a basic little x in here. We have 5x. That's a polynomial, so it won't be too tough. But let's go ahead and just practice that u substitution. And we're going to say that we're going to have let u equal to, set it equal to 5x, that inside function. And then if that's the case, then u prime, well, the derivative of 5x with respect to x is equal to just 5. So if f prime of x, or the derivative of f of x, is, with this u substitution, equal to u prime over u, then we just simply have 5 over 5x, and 5 divided by 5 is equal to 1, and we just have f prime of x is equal to 1 over x. So here we have another example. It looks a little bit more complicated, but 5x is a polynomial. We have 4x squared plus 7 is another polynomial, so I'm going to just step out and let you practice this u substitution on your own. So not only was that very straightforward in the end, we didn't even have any algebraic simplification we could do, so really this was even less work than this one. So let's get on to some examples that a little bit more involved. Okay, so we have over here the natural log of 2x minus 1 cubed. Pay attention to where this parentheses is, because if it was the natural log of 2x minus 1 to the third power, then we would be able to use some of those properties of logarithms that I talked about, which is we could take this 3 and move it out front and write it as 3 times the natural log of 2x minus 1, which would maybe save us from having to do the chain rule. But we don't have that option, and actually we're going to be using the chain rule to find the derivative of this problem. Now over here, I have a lot more going inside the natural log function, and I'll be able to use some of these properties, and I'll need to use some of those properties. Well, I don't need to. I could make things more difficult on myself, but to separate what's inside there, to finish that problem, use some of the properties to expand that natural log function before working through it. But here, we're going to take the 3 and use a chain rule. So it's going to be bring down that power, move it out front. So we have 3 times the natural log of 2x minus 1 squared. You know, we're going to bring that power down and reduce it by 1. But this isn't just, x cubed. It's a lot of something cubed. So we have to follow through the chain rule, which means now we have to multiply by the derivative with respect to x of the natural log of 2x minus 1. Chalk down! Okay, so now we get into a situation where we look very similar to where we were before, which is we need to work out this natural log, the derivative of this natural log of 2x minus 1. So u is equal to 2x minus 1 u prime is therefore going to be equal to the derivative with respect to x of 2x minus 1 is just going to be 2. So we have 3 times the natural log of 2x minus 1 squared times the derivative of this is going to be u prime over u, so it's going to be 2 over 2x minus 1. Okay, well there's not much left that's going to be able to be done except maybe just put this over 1 so we can see the numerator and denominator of these two values are now fractions that are getting multiplied together. We have 2 times 3, which is equal to 6, times the natural log of 2x minus 1 squared over, well, just 2x minus 1. Now don't be tempted to think that you can cancel out this 2x minus 1 because this 2x minus 1, the numerator, is inside the math function of the natural log. So that's it, unless I've made a mistake. Just checking, no. Nothing else can be done to simplify this, and this is equal to, oops, I guess I got to talking and got a little bit sloppy with my notes. Starting here is where I started to work out the derivative, so, and I'm off the camera, that's f prime of x all the way down until we get our final answer. Yeah, sometimes when I'm talking and thinking and writing at the same time, I sort of make small mistakes and I get, well, I try not to get sloppy or careless, but these are going to get longer and longer as we go through these examples, and you need to be very meticulous with your work, showing every step. It's going to reduce the amount of small mistakes or careless mistakes that you make. And me forgetting to write that f prime or that derivative of f on the line where I started doing the derivative, working it out, you know, I could have done many, many lines of work on up and lost track where I was and put the wrong notation somewhere and have a wrong answer. Okay, for our next example, we have f of x is equal to the natural log of x squared times the square root of x cubed minus 2. Now inside this math function, this natural log function, we have two factors. And not forgetting, of course, that radicals are a grouping symbol. So we have two factors being multiplied together inside our natural log. So, like our property page said, the natural log of AB is equal to the natural log of A plus the natural log of B. So we're going to expand this out. So we have f of x is equal to the natural log of x squared plus the natural log, and I don't like working with radicals inside my math work, so we're going to wrap this in parentheses, write x cubed minus 2, and we have no parentheses or powers inside here, so that's going to be raised to a power of 1, and we have an index of 2, so it's going to be raised to the 1/2 power. Okay, this particular term, just to point this out, it's not really that important for this particular question, but sometimes when you use the power property to take these exponents and bring them out, you're changing the domain of that function. The natural log of x squared, I can plug any value in for x that I want except for 0, because even if I plug in a negative, remember the domain for the natural log function is 0 to infinity, if I plug in a negative value, the first thing that's going to happen is it's going to get squared, which makes it positive. And that would mean I could apply the natural log function to it. If I bring the 2 out front and write it as 2 natural log of x, that natural log of x now has a domain of just 0 to infinity, not all real numbers except x can't be equal to 0. So you need to be aware that as you drop these exponents down out front, you could have some issues with domain, like if you're graphing or something like that. So just be aware that as you do your work, you know, there's over hundreds of, probably well over 100 problems in your calculus book, and they throw some twists in there at you sometimes. So I'm going to go ahead and leave that power of 2 up there, and I'm going to bring this 1/2 down out front just to make the finding the derivative process a little bit simpler. And we have f of x is equal to the natural log of x squared plus 1/2 times the natural log of x cubed minus 2. Okay, so now what? Well, we're going to just simply have two different u substitutions. We've got an inside function of x squared and we have an inside function of x cubed minus 2. So we have u is equal to x squared and u prime is equal to 2x. We have these other inside function, let's get a different colored chalk here, is equal to x cubed minus 2. So w is x cubed minus 2, which means w prime is equal to 3x squared. And if I wanted to be out, realize I wasn't doing this with some of my simpler questions as we get up into the harder ones, but if I just wanted to write function f temporarily with this temporary u substitution, we could say that, you know, this is now the natural log of u plus 1/2 the natural log of w. I realized I wasn't actually writing that line where I put the substitution in and then reminded you that the derivative, now that we start to work out the f prime or the derivative of f, the derivative of natural log of u is u prime over u. I just wanted to show that sort of super detailed substitution, or work one more time, excuse me. And the derivative of the natural log of w is going to be w prime over w. I'm going to go back to just sort of writing it like I did this example where I just verbally said it and wrote it. So u prime is 2x and u is x squared. And w prime is 3x squared. And w, again, is x cubed minus 2. And get that in terms of x back in there. At this point, all we have to do is clean things up. So to just take a couple of seconds off the video, I'm going to step out and algebraically clean this up and see what our final answer is going to look like. There we go. What did we do? We did a little cancellation, we found some common denominators, distributed and combined like terms, and we have f prime of x is equal to 7 cubed minus 8 over 2x to the fourth minus 4x. Next examples! Now with these two examples, we're just continuing the u substitution, so I'm not going to talk through every single step. These I'm going to just barely start this one for you and step out and reveal the solutions step by step, so you can either watch them be revealed or, better yet, pause the video and try them on your own to make sure you're totally getting this. Over here, it seems a little funny that we have the natural log of x cubed, but that just simply means, well, that our inside function is going to be the natural log of x cubed. And hopefully at this point in the video, you can just look at this maybe now with the pattern and identify what u prime is. And if you can, if you still need that u substitution, you can just sort of focus on this as your own separate little problem and say maybe, well, let my inside function w be x cubed, and then w prime maybe is 3x squared, and just work it out in really, really small incremental steps that way. Over here we just have another inside function, natural log. It's x plus the square root of x squared plus 4 this time. So we're not going to be able to separate or expand this natural log function, because the property was for expanding a log or natural log, these had to be factors and not two separate terms. So you're going to have to deal with all of this as your inside function. So let's see what those solutions look like, one step at a time. So with this one over here, we had a u value that when we found u prime, we had to, of course, use the chain rule. And we had a 1/2 from the power out front, reduce that power by 1, and we had 1/2 times, or 1 plus 1/2 x squared plus 4 to the negative 1/2 times 2x, the derivative of the inside function, the derivative of x squared plus 4. The 1/2 and the 2 cancel out. we need to drop that negative 1/2 into the denominator, or we can, and write it now back into a radical form, because at this point, just besides finding common denominators and such, we're not going to really work with it much. This 1/1, we need to find a common denominator, of course, so multiply top and bottom by the square root of x squared plus 4. We have it simplified into a single term, and that way when we write it as u prime over u, when you have a fraction over a fraction, that of course means a division symbol, and you can change the division of these two fractions by multiplying, right here, by the reciprocal of the second fraction, which is going to be our denominator. And when we do that, at least the way I have it written, we have the square root plus x and x plus that square root. And of course, addition is commutative, so it doesn't make any difference. It's still going to come out to be the same answer, and they cancel each other out to be a value of 1. Rationalize the denominator, and bada bing, bada boom, y prime is right there. So our next two examples, we have one with an absolute value function and trig functions mixed in with it, and our last example dealing with a little bit of implicit differentiation. Bam! Last board. We got y is equal to the natural log of the absolute value of sine x over cosine x minus 1. And you know, remember when we first started doing derivatives, finding derivatives with the absolute value function gave a pretty special little case, a set of challenges that we had to deal with. But like our note showed, that if I want the derivative of the natural log of the absolute value of u, it's just going to be u prime over u. It's just going to work out just the same as all these other problems. So we're going to expand this natural logarithm first to separate the division to make this a little bit easier. So we have y is equal to the natural log of the absolute value of sine x minus the natural log of the absolute value of cosine x minus 1. Well, in here, our u would be sine, and our u prime, the derivative of sine, is going to be cosine. So we have y prime is, okay, u prime over u, and u is sine over sine x, and u prime, the derivative of sine, is cosine. Minus, now here, our u is cosine x minus 1, and our u prime, well, the derivative of negative 1 or a constant is 0, so just the derivative of cosine is negative sine x. Now, we got a negative, and then we have a negative in our numerator, so subtracting a negative is addition. So we have y prime is equal to the cosine of x over sine x plus the sine x over the cosine x minus 1, and if you would like to write that as a single term, I don't think it really simplifies much, yeah. If you want to write that as a single term, you would just find common denominators, but I'm going to just leave it as our two separate terms. Now over here, we have a different, slightly different direction, just reminding you of how to do implicit differentiation. We have 2y plus the natural log of x squared times y is equal to 6. So instead of trying to isolate y and just doing the regular derivative process, let's go to this implicitly. So we're going to find the implicit differentiation in terms of, or with respect to, x. So we have, well, let's see here, let's make life a little bit easier, and again, let's use our properties of logarithms, natural logarithms, same thing, to separate this multiplication. And we have 2y plus the natural log of x squared plus the natural log of y is equal to 6. And working through this now, the derivative of 2y with respect to x is going to be 2, and normally it would just be like 2 if it was like the derivative of 2x would be 2, but then again with this implicit differentiation we have 2y prime because we're finding the derivative with respect to x. It'd be dy over dx, which we can write as y prime. Over here we have plus. Now u is going to be 2x, and the derivative of u, did I just say 2x? I was thinking of the answer. X squared, and the derivative of x squared with respect to x is going to be 2x. So we'll have some cancellation going there. This x in the numerator and one of these two x's in the denominator will cancel out. And then over here we have plus the natural log of y. Okay, well that means that for this u substitution, or you could call it w since we're working in the same equation if you're actually writing this out now, Our u substitution, or u or w, whatever you want, variable you want to assign it, is y. And the numerator is that u prime, which is going to be, well, the derivative of y with respect to x is dy over dx, or we can just write that as y prime. And then over here, the derivative of a constant is equal to 0. So I just really need to work this problem, get it solved for y prime. So I'm going to first take the 2 over x and move it to the other side, and we got 2y prime plus y prime over y is equal to that 2 over x, which is positive. We're going to bring it over with subtraction, so minus 2 over x. I can factor the y out now, but I'm going to go ahead and get this y out of the denominator. So I'm going to multiply both sides of the equation by y. That is going to give me 2y y prime. Over here in the second term, the y's are going to cancel out, just leaving me with y prime. And then over here we have negative 2y over x. Each of these terms have a y prime, and that's what I'm trying to isolate. I'm trying to solve for y prime. So I'm going to factor that out, and we get, and I'm probably going to run out of room here, we have y prime times 2y plus 1 is equal to negative 2y over x. And our last step is to divide both sides of our equation, so we'll just use purple, over by 2y plus 1. And when we do that, of course, this cancels out, and our final answer is going to be y prime. I mean, I know you can see it, but negative 2y over, yes, I break my chalk fairly often, x times 2y plus 1. And just to make sure, since I'm talking and writing and thinking all at the same time, yes, I'm right. So, I'm Mr. Tarrou. Now it's time for you. Go do your homework.